Well, welcome back. And so this is the second lecture on streaming. I will talk about, and my name is still Michael, I will talk about frequency moments. So I'll finish the discussion of frequency moments that we started last time and talk about the so-called heavy hitters problem. And this will be the count sketch method that Ilya mentioned in his lecture. Good. Okay, so first let me just briefly remind you what we're interested in. We're interested in designing linear sketching primitives for analyzing huge data sets. Namely, we think of a data stream of items as a vector x. Think of x as the frequency histogram. And we are interested in designing these sketching matrices S. So this, if x has dimension m, then S will have n columns and a small number of rows, which is the sketching dimension. So we're designing algorithms that allow us to maintain a matrix vector product under updates to the vector x in the stream. And from the right-hand side, from this matrix vector product, which is just m numbers, usually polynomially bounded numbers, we can extract useful information about x. Good. And we're trying to get to graph sketching, which we will do very soon. Good. So in this lecture, frequency moments and heavy hitters. Let me remind you what the setting is for the frequency moment problem. And the setting is the following. Well, we're given a large data stream of items, and we think of x as the frequency histogram of this stream. We want to approximate its L2 norm. And we want to design an algorithm that uses a small amount of space and approximates the L2 norm of x under increments and decrements to various positions of xi. So if you forgot what the setting is, let me show you this picture again. So here, we sort of say we have a universe of size 10. So in the stream, we get numbers between 1 and 10. The stream is shown here. And x is the frequency histogram. So this is a vector with integer entries in Rn. And as the stream comes in, the arrival of item I is basically just an update to the ith entry of x. Good. So this is to remind you what x is. Our goal is to approximate the L2 norm squared of x. Good. Now, what is the solution that we designed last time? The solution was the following. Well, so note that trivially you can't do this because you want the sum of squares of xi, and xi's are updated in the stream. What we do is take the vector x and basically just compute a dot product of x with a vector of random signs. So note that this is very similar to Johnson-Lindenstrauss that Ilya presented in the previous lecture, where we were dotting the x with the random Gaussians. But in this case, we will dot x with random signs, and we'll see what the fine differences are. Okay, so this is our solution, and this is due to Alon, Matthias, and Zegedi from '96. So let R1 through Rn be IID random variables. The Ri is just a random sign, independently +1 and -1 with probability 1/2. Then the algorithm, sort of our basic algorithm, and this will not quite work, we'll fix it in a second, will maintain basically a dot product of R and X. Our algorithm will maintain the counter Z, which is the sum over I from 1 to n, Ri times Xi. So note that as we think of X as being initially 0, it's easy to initialize. So we initialize Z to 0, and then as data items I, J, etc. come in the stream, we simply, when I comes, we just add Ri, the sign of the ith data item, to Z. So this is doesn't mean that we compute Z, but rather we start with 0 and maintain Z as the stream evolves. Okay. What we want to output is just Z squared, and I want to claim that Z squared is sort of close to the L2 norm squared of X with pretty good probability. And let's see how we can prove that. Good. So we have a quantity which is the L2 norm squared of X, and we have a randomized estimator, which is Z squared. So how do you prove that Z squared is close to X? Well, one way of doing this is to show that, well, first, Z squared is an unbiased estimator of the L2 norm squared. Just compute the mean, then bound the variance, and show that the variance is small compared to mean squared. This is exactly what we'll do. I showed this calculation last time. Let me briefly recap it. Well, we look at the expectation of z squared. Z was just the sum of Ri xi. We expand this sum as a double summation. Well, then we look at this double summation and note that there are two types of terms. There are cross terms, that is products Ri, Rj, xi, xj, when I is distinct from j. And those vanish because the Ri's were assumed to be independent. And the mean of each Ri is 0. So the only thing that remains is the diagonal terms. Okay, any questions on the setup?
Is this term the reason why you pick these Ri's in the end? Because this is strange. Why do you pick this positive or negative signal? Because you're changing the input, right?
Oh, I see. I see. So the question is sort of what is the intuition for, like, how did we come up with plus minus ones? Yeah, the question was why do we dot with plus minus ones and not something else? The answer is the following. Plus minus ones are not that important. As Ilya showed in the previous lecture, you could have used Gaussians. Really, for this type of calculation, we could have used a reasonable random variable with variance 1 and 0 mean. Right, and this is just an example of a simple random variable with variance 1 and mean 0. And so this fact that we are multiplying each entry of x by a 0 mean random variable is exactly what lets us approximate the L2 norm. Because sort of what happens is that this z ends up being a random variable whose mean is 0, so the only thing that matters is the variance, which is exactly the manifestation of the fact that the cross terms vanish. And so the fact that our i's have 0 mean exactly gives us the diagonal terms stay. Good. Any other questions on the setup? All right. Good. So our estimator is unbiased, which is excellent. So now let's bound the variance. So we want to prove that our z squared is actually with pretty high probability close to its mean. Well, the variance of z squared is the expectation of z to the fourth minus the expectation of z squared squared. So we need to bound the fourth moment of our z. What is the fourth moment? Well, it's the expectation of this product of four sums over I from 1 to n, Ri xi, same thing with Rj xj, Rk rq, etc. Well, this is a very similar analysis. We just think of what type of cross terms do we have here. And what kind of terms do we have? Well, for example, we have n terms where we only have one xi that appears with power 4. And so the corresponding sign also appears with power 4. So what this gives us is the summation over I from 1 to n of xi to the fourth. And the other type of terms that we have is the cross terms, where there's actually two distinct elements, I and j, and they appear with power 2. The powers have to sum up to 4. A simple but careful counting will reveal to you that this is exactly how many terms of this type you have. So it's a summation over I strictly less than j, Ri, Rj, xi, xj, the whole thing squared, and there are 6 such terms. You just do some counting. Okay, good. So this is the expectation, because Ri squared is 1, the same for Rj. Okay, so then the remaining terms are the terms that in which at least one Ri xi, and I really care about the Ri, appears with power 1. And those are 0, because the expectation of Ri is 0, and the Ri's were independent. Good. So hence, the fourth moment is exactly equal to this quantity. It's the sum of the fourth powers of xi plus 6 times these cross terms. Any questions? Okay, good. So now let's just do some computations. We understand the fourth moment. Well, now we take the second moment and subtract. What happens is that the fourth moment is this. It's the sum of the fourth powers plus 6 times the cross terms. We're subtracting the L2 norm squared. So, well, this term also has a diagonal term, so the xi's to the fourth cancel. Whatever remains of the L2 norm squared is twice the sum over I less than j of xi squared, xj squared. All in all, if we do the constants right, we get that this is at most 4 times the sum, and in particular at most twice the L2 norm squared.
Why is the first at most equal?
It's actually equal. So in particular, at most holds. That's the only thing we care about. Good. All right. Good. So let's see. Are we happy? And what do we do next? Well, we know the mean of z squared, and we have an upper bound on the variance. What we do is just apply Chebyshev's inequality. Chebyshev's inequality says that for every t at least 1, the probability that z squared deviates from its mean by more than a t factor, t times the standard deviation, is at most 1 over t squared. So this is what we get. So the probability that z squared deviates from the L2 norm squared by more than twice t times L2 norm squared is at most 1 over t squared. Is this any good? Does anyone see any issues with this? Is this useful? Should we declare victory yet? So by Chebyshev's inequality, we know that for every t at least 1, the probability that our randomized estimator deviates from its mean, and the mean is the square of the L2 norm of x, by twice t times the L2 norm squared is at most 1 over t squared. What would you set t to? So what is the smallest t that would give a useful bound? Hmm? 2? Why is it 2?
Because if you take 1, you would get the 1.
Yeah. Oh, I see. Yeah, good. So basically what we want is the right-hand side to be less than 1. Otherwise, we're not getting a useful bound. If you want to make the right-hand side less than 1, then what? Well, then t had better be at least 1. But then the only thing that we're precluding is deviation by more than a factor of 2 of the mean. So this does say that our estimate doesn't overshoot. But it could easily be 0 by this rationale. So it's a little bit early to declare victory. So the variance is too high. So this is not good. So what can we do to fix it? Chernoff. Oh, I see. I don't think that's not going to work, right? No, that's not going to work because it's not going to work. Yeah. So we have an estimator. It has the right mean, but the variance is too high. What do we do? Take many of them and just average. And that's exactly what we're going to do. So we'll reduce variance by averaging. Okay. So here's the actual algorithm. Instead of maintaining 1z, we'll maintain kz's for k to be set in second. And each z is what? It's a dot product of xj with a fresh vector of random signs. And so our output is just the average of zi squared. Good. So what is the variance? Okay, so the mean of this a is exactly correct. We're averaging. The variance is exactly 1 over k fraction of the variance of our original z. So, because they're independent. So now the variance is at most 2 over k times the fourth power of the L2 norm. And now by Chebyshev's inequality, we're already getting something useful. We can set t to be, say, 10. So we reduce the failure probability to about 1 over 100. Yeah.
Do you know if median would work instead of averaging here?
I do not know. Median. I see. I don't know. For Gaussians, would it work? Would it give non-trivial?
It probably would work, but for non-trivial reasons, I suspect.
You need to understand then sort of what's the median of a Gaussian distribution. Right. Is it any better than what Chebyshev gives you? Yeah, it's an interesting question. Yeah. Okay. Good. So basically now let's just set t to be 10. So the failure probability is at most 100, 1 over 100. And now we still get to choose k, the number of repetitions, to have a useful bound. So if we choose k to be on the order of 1 over epsilon squared, then we will get that the probability that our answer deviates from the L2 norm by more than an epsilon factor is at most 1 over t squared. Okay, good. So this is the algorithm. We dot our vector with random signs and then look at the mean and average 1 over epsilon squared times. Now, the question is, how many do we need, again, coming back to this question in the first part of the lecture, how much space do we need to store the RIs, the vectors? And the answer is not much, because if you rewind the analysis, what you will see is that the only thing we used is a fourth moment calculation. So we only wanted to, in order for this calculation to go through, we only wanted independence of 4 distinct RIs. So 4 wise independence is sufficient. And we can generate 4 wise independent random signs in order log n space. Okay. Good. So at this point, what we have is an...
Also need to account the fact that we actually generate not just one string of random signs, but many of them.
Yes, yes. What we have is order 1 over epsilon squared such RIs. So the total space complexity will be 1 over epsilon squared times log n. Yeah. Good. All right. So what this gives is an algorithm with failure probability 1 over 100. What if I want a better failure probability? Oh, as in smaller but failure probability. How do I do that? What should I tweak in this algorithm to have a better failure probability? By the way, I think there's a typo here. This needs to be a root k. So how would I choose k? So how many? So how do I reduce the failure probability?
Increase k, decrease t.
I see. So I could increase k, right? But what if I want failure probability delta? Then I would need to reduce to the trivial way, if I were to use Chebyshev's inequality, would be to make k 1 over root delta. Well, that's a pretty bad dependence on delta if I want failure probability, say 1 over poly n, 1 over n to the 10. The way to fix it is to use the median trick. So namely, instead of just averaging many, many times, what we do is we get one estimator whose variance is small enough so that with probability at least 99 over 100, it gives us a epsilon approximation. Then after that, we choose order log 1 over delta copies of this estimator, and we just keep order t copies of this algorithm in parallel. And all these copies of the algorithm will use independent random variables, independent signs. After that, we take the median of the answer. So what is the probability that the median will fail to be a epsilon approximation? Well, I claim that if the number of repetitions is only on the order of log 1 over delta, then the median fails to be good, and by good, I mean an factor 1 plus minus epsilon approximation, with probability at most delta. Why is that? This is by Chernoff bounds. Well, we have capital T copies of our algorithm. So let me define an indicator random variable y sub t, which is equal to 1 if the tth algorithm fails and is 0 otherwise. So now the probability that the median of what we, the median of the answers that we computed fails to be a factor epsilon approximation is at most the probability that at least half of our algorithms fail. On the other hand, each of the independent copies fails with probability 1 over 100. So by Chernoff bounds, the probability that at least half of these algorithms fail is exponentially small in how many repetitions we did. Okay. Questions?
Could you actually show the red part once again? So if we would like to reduce the failure probability
So I have a typo here. So this should be root k, right? So this is like the root of the variance. Right.
So the probability of failure here depends on t. So
Yes, yes. I would need to make t, right? So if I want 1 over t squared to be say delta, then I would need t to be root delta, or 1 over root delta, right? So I would have to make t 1 over root delta. To compensate for that, I would need k to be, yeah. Okay. Good. All right, so this is the median trick, which is a standard trick in streaming. So what we did was we designed one estimator who had the right mean, but had too bad of a variance. Then we averaged sufficient number of times to reduce the variance sufficiently so that with constant probability we get a factor of 1 plus minus epsilon approximation. After that, it becomes inefficient to average further. What we do is just do independent repetitions and take a median. This lets us reduce the failure probability much better. Okay. So there's one downside to the median trick, and which is you don't quite get a Johnson-Lindenstrauss type result. So you don't get you don't get an embedding into our into Euclidean space, because you sort of get a nonlinear embedding because you're taking medians, so it's hard to work with. But as Ilya showed in his lecture, if you replace these random signs by random Gaussians, and basically you have a lot of independence, then taking medians is not important. And the things just concentrate so well that you can just average log 1 over delta times, and you'll get the right result. Okay, good. So what did we get? Here's a summary. We designed a linear sketching matrix. It's a matrix with a small number of rows, and the number of rows was about 1 over epsilon squared log 1 over delta. That's because we did log 1 over delta repetitions of the basic algorithm, and each basic algorithm was keeping order 1 over epsilon squared dot products with random sign vectors. And if you look at the right-hand side, so the sketch matrix times x, and do some nonlinear operation. So in this case, this was a median of you take blocks of the B vector. You compute L2 norms squared of the blocks and then take the median of those. Then we get a 1 plus minus epsilon approximation to the L2 norm squared of our vector x. And this is known as the AMS sketch. So note, again, so these are linear sketches, so they're easy to maintain in the dynamic streaming model. Good. So this is the AMS sketch. And in the rest of the lecture, I would like to look at a different primitive, which is heavy hitters. Yeah.
How are you going to store this arrays in log n?
Ah, good. So the question is, how do you store the RIs in order log n bits? So you need to, you want 4 wise independent random variables. So think of a polynomial over a finite field, and sort of degree 4 or 5 polynomial will suffice. 5, I guess, right? Yeah. So you take a polynomial of degree, a random polynomial of degree 5, and your RIs will basically be the evaluations. The signs will correspond to evaluations of your polynomial on the endpoints. So generally, if you want t-wise independence, then you sort of take a polynomial over some finite field of degree t plus 1, right? No, just t. Yeah, yeah. T minus 1 even, right? T minus 1. You want t coefficients. Yeah.
So that's the reason why you want signs instead of Gaussians, to be able to generate them efficiently.
Yes, exactly. Yes. So note that the signs are sort of more efficient to generate, and in particular, it is possible to show that with random signs you also get Johnson-Lindenstrauss type results, and this is also known as the database-friendly Johnson-Lindenstrauss transform, because signs are much easier to generate. Yeah. So in particular, if you have log like log 1 over delta wise independence, you'll get failure probability log 1 over delta even without the averaging. But such random variables will be harder to generate because you will need polynomials of higher degree. Other questions? All right, good. So the heavy hitters problem, and so for the heavy hitters problem, we'll be in the following setting. Let me again remind you of this data streaming setting, and I'll show you what the problem is. So we have capital N data items, so I'll need to change notation a little bit. So we'll have capital N for the number of items in the stream. And for this problem, the items will come from a universe of size little m. So we'll come up in a little bit. Our task will be to take a single pass over this data stream of items. And at the end of the day, we'll output k most frequent items. So this is the informal statement. We'll make it formal a little bit in a little bit. So we'll output the items that occurred most often in the stream. Good. And we will achieve small storage, namely to solve this problem. And I didn't tell you sort of the approximate nature of this problem, what we are actually solving, but we'll get space order k log n for some constant factor approximation, whatever that means. Good. So here's the setting. Again, we have a stream of items, and we have this histogram, frequency histogram. And for example, if our k is 1, we want the most frequent item, then the item 3 is what we want. Yeah.
Isolated variables, again, bounded by m. Is values.
The sum, yeah. So the number of elements in the stream is upper bounded by capital N. It's exactly equal to capital N. So like the height of these bars is at most n in particular, but the sum of the heights is exactly n.
Here you k as a constant.
Yeah, think of k as a constant. It can be whatever you like. Your space will increase with k. So if k is 1, then we'll run in space order log n. If k is larger, then the space will just scale linearly. Okay. Good. Okay, so let me again show you the motivation. So first, the motivation in terms of the internet routers. Again, you have a router, and you're monitoring traffic. There's a lot of packets coming through the router, and at the end of the day, you have this huge traffic matrix, and there's a number of non-zeros there. But now, what you want is not the number of non-zeros, but you want to understand. Oh, so what were the dominant flows, so-called elephant flows? And for example, in this situation, well, we had a few source destination pairs that just exchanged a single packet, and 2 of them exchanged 5 packets and 4 packets respectively. So say if our k is 2, then we want to know what exactly was the source destination pair. What were the top guys who were communicating the most? Good. So the trivial solution would be to store all distinct IP pairs. And this will lead again to complexity that is in the worst case linear in the number of source destination pairs. We will get order log n complexity if k is 1, if k is constant. Again, the same motivation for estimating search statistics. If you have search queries on Google, you want to know what is the most popular query, or what are the top few most popular queries. And count sketch will solve this problem quite efficiently for small k. Okay, good. So this is what we want. Does anyone have any questions about the goal?
How much does the problem change if you might have items that, okay, they are not similar, but for your output, you could say that, okay, if I'm mistaking this one for this one, that's fine. So I have an approximation on how these items are aligned, so to say.
I see. So you're saying that you want to also say that 2 looks a little bit like 3. You want to confuse 2 with 10, but 2 and 3 is fine. I see. So this type of solution won't really work for it. So you would need some, yeah.
There is a recent actually paper that studies precisely that, like heavy hitters and distinct elements under uncertainty by Qin-Zhang. So I can send the link.
Oh, I see. Yes, I've seen this one. Yes, it's in SIGCOMM or something. Yeah. Okay. Yeah. Interesting. Yeah. Oh, yeah. So for the case when there is some metric.
Yeah.
Well, this is for distinct elements, though. That's not sort of tough. Yeah. Okay. But it sounds very relevant. Yeah. Good. Yeah. For this this type of approach, you think of the items as just distinct. Yeah. But good. Okay. So here's what we want. We want to design a small space data structure, and I will call this data structure find top. Find top is a data structure that allows you to scan a stream S, and at the end of the day, or rather at every point in the stream, is able to give you the top k most frequent items seen so far. So this is what we want. Well, it turns out that before we design this data structure for find top, it's pretty useful to design a point query data structure. And once we have it, we'll get our goal. So let me tell you what this point query is. It takes the stream as input, it scans the stream and maintains some kind of a small space representation. And when it's given a query item I, so one of the items arriving in the stream, it's able to return the number of times fi, the item I appeared in the stream. So here I will call the frequency of the item fi. Okay. Yeah, so we want to find the top k, but I'm saying let's first design an oracle. It sort of scans the stream, remembers something about the stream, and then when you give it an item, it just tells you how many times did it occur so far. And as we'll see, these exact primitives are a bit too good to be true. They're actually not, it's not possible to design them using small space, but it will be useful to think about this one. Okay, so fi is the frequency of item I, and for simplicity, let's assume that the frequencies are decreasing. So f1 is one is the most frequent element in the stream. So sort of what we want to design is this point query primitive in space k log n, and that's impossible. Why is that impossible? Well, just think of a stream of items where sort of every item appears, say, 1 or 2 times, or really 0 or 1 times. You would have to remember, you would have to invest about 1 bit of information for each such item. So you can't really do it. Because of that, we will not solve the exact problem. We will solve an approximate problem. And the problem will be this. It's called find approximate top. So now it has 3 parameters, the stream, the k, and a precision parameter epsilon. And what we want is to return a set of k items such that the frequency of all the items that we report will be at least 1 minus epsilon times fk. You know, the fk is the least frequent of the top k items. So if epsilon is 0, then this is exactly the precise problem of returning the top k items. But if epsilon is some constant, so think of 0.01, this is an approximate, relaxed version of the problem. It will be easier to solve. Well, similarly, before we design a primitive for this problem, what we will do is design an approximate point query primitive. It again takes the stream, an item I, and a precision parameter epsilon, and it processes the stream, and then if given an item I, at every point it will be able to report an approximation to the number of times we have seen I in the stream. So we'll call this f hat I. And the guarantee will be that f hat I is additively close to the true answer to fi. So f hat I will be between fi minus epsilon fk, the frequency of the kth most frequent item, and fi plus epsilon fk.
So that approx point query is good for every find approx top related to the k. Yes?
Say again?
Approx point query has parameter k.
Yes. Yes, yes. It has this sort of built-in parameter. Good. Good. So basically what this will let us do, and we'll see, this will let us find the most frequent items, but only under an assumption. Only under the assumption that these frequent items actually contribute a bulk of the stream in some sense that we will see in a second. Okay, so here's how we will design the solution. Well, first I will convince you that looking at this approx point query primitive first is a good idea. So namely, I will show that if I have a point query primitive or an approximate point query primitive, then finding the top k items is easy. Then we will design a very simple basic version of approximate point query, and then we'll design the final count cache algorithm. Okay, so let's first do a trivial exercise. So suppose that k equals 1. And suppose that we have these exact point query primitives and we want the exact top k. And then I'm claiming that I can use the exact point query to find the most frequent element. Of course, exact point query requires pretty much storing the entire stream. But we'll see that sort of the same logic will carry over to approximate versions of the problem. Okay, so I'm getting these elements in the data stream, and I'm also maintaining this point query data structure. Besides that, I will maintain two variables. One variable that will store the current maximum element, sort of the most frequent item seen so far, and another variable that stores the frequency. So as I'm scanning the stream, I will do the following. Well, if I get an item IP, I'll just ask my primitive, well, how many times did this item occur so far? Well, it gives me the frequency count for this item. And then I check. If this item is what I'm currently storing, its count only increased. So I'll update the count and continue. Otherwise, I'll just, if I was storing nothing, I'll store this item. And if what I was storing so far is less frequent than the item that just arrived, I'll just store my item IP and with its count. It's really saying a very simple thing. I'm just basically looking at the stream, and at every point I'm saying, I'm getting a new item, I'm asking, oh, is this the item that I should be storing? So I have a very powerful oracle. If it tells me yes, I just do it. Okay, so why does this work? Well, at every point in the stream, this current maximum is either null or the most frequent element seen so far. Okay, so how about k bigger than 1? Well, this is what we do. It's the same thing, but we'll just now store a heap of at most k items. And the key in the heap will be the count. So again, as an item comes in, I check what the frequency of the item is. And I check if I'm storing the item in the heap, I'll just update its key to the current frequency. If the heap still has some space, I'll just add this new item to the heap. And if not, I'll look at the least frequent item that I'm currently storing. And if it's less frequent than what just has arrived, I'll swap them. I'll evict the least frequent item, and I'll put in the item that just arrived. All right. Well, why does this work? Well, let's look at our top k, the most frequent items, and let's just look at the last occurrence of each such item. So when each such top k item occurs for the last time, what are the possibilities? Well, it will definitely be inserted into the heap H if it was not there in the first place. Why? Because it's one of the top k frequent items. The heap contains k things, so the least frequent item in that heap will be less frequent. And after that, it's never evicted because the heap has capacity to store k items. It's one of the top k. So somebody else will be evicted if anything. All right, so this is extremely simple. The question is, why do we care? Because we know that point query, the exact point query primitive, cannot be implemented in small space. Well, the point is that a very similar reduction shows that if you have an approximate point query primitive, then you can use it in the exact same way to get an approximate find top. So we're scanning the stream, and now whenever an item arrives, we ask our oracle to give us an approximation to the count. It gives us some f hat, and we just pretend that this was the right count, and we update the heap accordingly. One needs to squint a little bit, but I encourage you to think this through, and you will see that this will basically be, you'll get the same guarantees, and the guarantee will be that the items that will end up in the heap will have frequency at least 1 minus epsilon times the frequency of the least frequent item. So whatever the error is on this f hat, it will propagate into the guarantee in this reduction. Questions?
So could you remind what we assume about the error? So is it like?
So we assume that the error is that this f hat is additively close to the actual frequency. So if item I arrives, it actually occurred with frequency fi. I'm given f hat. Well, then the question is, how far is f hat from fi? And what we will get is a primitive that ensures that this fi minus f hat is bounded by an epsilon fraction of fk. I don't think there's any chalk. Ah, good. Thanks. Yeah, so basically what we will design is some primitive that gives us fi hat such that fi hat minus fi is at most epsilon times fk. So this is what we will ultimately get.
And this is for approximate point.
Yeah, this approximate point query, given an item I, will spit out an estimation of how many times fi occurred so far. There will be some error on this estimate. This will be an additive error, and the error will be an additive epsilon times the frequency of the kth most frequent item. So basically, even if fi is fk, then you're still getting this 1 plus minus epsilon approximation. Yeah.
What kind of heaps we are using? We can use it's classical balanced trees, or maybe something special.
No, all I want is just a heap that can. This is just for efficiency. Right? So if you only care about the space complexity, you could.
It's not important.
Yes, this is just to be efficient. Right? Yeah. So if you want to efficiently extract something with the smallest key, then you would use a heap. But if you only care about space complexity, you could just store it in an array, and I just want to find.
Efficiency question is secondary.
Yeah, it's a nice question, but yeah, we're mostly dealing with space. Other questions? All right, good. So a moment of contemplation reveals that if we design this approximate point query primitive with parameter epsilon, that will give us the guarantees that I just stated on the frequency counts fi hat, then find approximate top will return us a set of k items such that the items that we return will satisfy fi hat is at least 1 minus epsilon times fk. So we might make some mistakes, but these mistakes will be sort of around the edges. If fk is the least frequent item that we care about, maybe we'll return somebody slightly less frequent, but it will not be much less frequent. All right. Good. So here's what we want to design. So now comes the actual content. We want to design this approximate point query primitive using a small amount of space. We want to observe a stream of updates, maintain a small space data structure, such that after observing the stream, if we're given an element I, so now our universe is 1 through little m, we want to give an estimate of how many times I occurred in the stream, so fi hat is supposed to be close to fi. There are several things that we want to specify still, namely, when I say small space, what do I mean? When I say it has certain quality of approximation, well, I sort of already said what I want, but I will need to set parameters. I'll need to show you how the quality of approximation depends on the space. And what is the success probability? Good. So we'll get to this in a couple of steps. And the first step will be to design a very simple version of approximate point query. It will not really work that well, but it will give us the main idea. And then we'll boost it by various tricks. Okay, again, so we're assuming that elements are ordered by frequency, f1, f2 through fm. This is our stream, and we are interested in the top k coefficients. It will be pretty useful to think of the stream as consisting of two parts. There's the head elements in the stream and the tail elements in the stream. And so the head elements, say k is 4, so the head elements will be the top k, we'll show them as green. So these are the most frequent elements, and the tail is all the rest. It's shown in red. So the tail will sort of provide noise in our algorithm. It will be the cause of our bad estimates. So first, I want to design a very basic estimate for the frequency count that will use only a constant amount of space. And then I want to analyze its precision. Well, the estimate will be extremely simple. It's actually pretty similar to the AMS sketch. What we will do is we'll first choose a hash function s because this is a random sign function. This hash function s maps our universe of data items, m, to plus minus 1s. And let's assume that s maps it uniformly at random, but 4 wise independence will suffice, or perhaps even 2 wise independence. We'll see. So this hash function will later we'll be able to substitute it with something that we can do in small space. Well, the basic estimate is just a single counter, call it C, initialize it to 0, then whenever an item I arrives, well, we do exactly what we did in the AMS sketch. We just add the sign of I, the sign of this data item, to the counter. And that's the process. Good. This is our data structure. Now, how do we answer queries? Well, if later, at the end of the day, we're asked, oh, so how many times did item I arrive? We'll just take the counter, we multiply it by the sign of I, and we return this answer. And I want to understand how good this randomized estimate is. It will not be entirely good, it will be pretty reasonable, and we'll make it better. Now, as before, how do we argue that a randomized estimate works? Well, again, we want to show that it's close to the right answer, that is Fi, the number of times element I occurred, with high probability. To do that, we'll first show that it's an unbiased estimator, so at least in expectation over the random sign function, this is exactly equal to Fi. Then we'll bound the variance, and then we'll have to spend time understanding the variance. Okay, good. So let's do the calculation for the expectation. So it's useful to rewrite this quantity a little bit in a slightly different manner. All right, so what was this counter? The counter was just the sum of the signs. As the data items were arriving, for positions p from 1 to n, we're adding up the signs of the item in the pth position. Well, this can be rewritten equivalently as the summation over all j in our universe of data items of fj, how many times it arrived, times its sign, and then sj, and then we're also multiplying by si. Now, here it's useful to split the sum into two parts. Naturally, we get what we actually want to estimate. That is, inside this universe of data items, there's the fi that we care about. And this fi is multiplied by si squared, which conveniently is 1. And then we have something that is the noise term, similar to the off-diagonal terms, the cross terms that we got in the AMS sketch. It's just the sum over all other elements in the data in the universe, fj, the frequency of the jth element, times the product of signs, sj and si. So these are random plus minus ones. So if I put expectations on top of this, I get fi plus the cross terms, and the cross terms vanish again. And as before, the mean is correct, the estimator is unbiased. So now let's invoke Chebyshev again. We want to understand the variance. So we know that the mean of the counter times si is exactly fi. What is the variance? Any questions so far, by the way? Seems to be a bit of very similar to the AMS sketch, so presumably it should be the same. Good. So what is the variance? Well, the variance is the expectation of our estimator minus its mean, the whole thing squared. Our estimator on the previous couple of slides, we just rewrote it as fi, which conveniently is its mean, plus the sum over all the other elements in the universe, their frequency times the product of signs. So the variance is what? Basically, fi cancels, and what we get is that what the variance is the expectation of the sum over all other elements j in the universe of their frequency times sj si, the entire thing squared. Well, this is good. Now we open it up again. We get a double summation. The square of the sum is the sum over j in the universe minus our item I, j prime of the same type, of the product of frequencies times the signs. So we put the expectation on top of this. We take the expectation of both sides. And what do we get? Well, as before, in this double summation, if j equals j prime, then we get what? We get fj squared times the expectation of sj times sj, but sj squared is 1 for all j. So this is a fixed, this is just a constant. On the other hand, if j is different from j prime, then the expectation of the product of the signs is 0 as before. Good. Good. And so what is the upshot? Well, the upshot is that the variance of our estimator is exactly the sum of squared frequencies over all the other elements of the stream. This is our variance. So by Chebyshev's inequality, we know that the probability that, say, our estimator is more than factor 8, deviates from the mean by more than a factor 8 times the standard deviation, which is the square root of the sum of squares of the other frequencies, is at most, say, 1/64. This is not bad. Now, actually, is it? Sorry, how good is this? The question is, we have some kind of a bound, but we know that our estimator for Fi is this close to Fi. Well, what is this? Is this good or bad? So the quality of the estimate depends on the sum of squared frequencies of the other elements in the stream. Okay, so what does that mean? Well, this means that we got an algorithm that works pretty well in estimating the most frequent item in the stream. Sort of imagine that the stream contains one item that is really frequent, and then all the others are kind of small. So here's a picture. So if this item 1 is the one whose frequency we're estimating, then things are good. Well, on the other hand, if we're estimating item 6, then we'll get a terrible error. Because the variance in the error will, in particular, include the contribution from the top one item, so we'll be way off. So this estimator estimates pretty well the frequency of the top guy, but really fails on the others. So the question is, how do we fix that? Let's fix this. And so this is the final ingredient that we need to get the count sketch algorithm. And the ingredient is this. Before applying this simple estimate, we will subsample the stream. And we'll do this by hashing the universe of items into a number of buckets. What we'll do is, if we're looking to find the top k elements, then we'll hash into order k buckets. Think of 100 k buckets. We'll look at the data items, the m data items, we'll just hash them. Then what we do is we run this simple estimator, but not on the entire stream, but on every single bucket. And to boost success probability, and so to reduce failure probability, we'll do something very similar to the median trick. We'll just repeat order log n times independently and take the median as the answer. Okay, so let me give you the intuition for this. The intuition will basically be this. So if we have, so imagine our stream, and think of the stream as having the top k coefficients, top k most frequent items, and they're large. So what we want to ensure is that most of the time we estimate large items from substreams that sort of look like this. There's this dominant item, the top k item there, and everything else is noise, is small. Then we get a good estimate. And now the small items, we will estimate from substreams that look like this. We want this estimate to not be contaminated by any of the top guys. And so if this is the case, then we'll be in a good shape. All right, good. So here are the main ideas. So first we run the basic estimate on subsampled or sort of hashed versions of the stream, and this is for reducing the variance. And then we take medians to boost the confidence of our estimates. Good. And so the hashing looks like this. So note that what we're doing is we're looking at our data universe of data items, and these are the top guys, the 1, 2, 3, 4, and the noise. We're just hashing them uniformly at random to a largish number of buckets, order k, and then run the basic estimate on the content of every bucket. So here's a picture. So for example, in this case, 1 and 6 got hashed together to bucket 3. So the subsampled stream, or the hashed stream that we'll run the basic estimate on to get an estimate for 1, just consists of 2 items, 1 and 6. So we'll get a pretty good estimate for 1, because it will only be contaminated by 6. Say the subsampled stream of 5 just contains of the items that hashed into bucket 5. This is a coincidence. Items 5 and 7. Okay.
What part do you repeat order log n times?
What do we repeat order log n times? Just next slide. Next slide. We'll basically perform this experiment. Yeah. One moment. Good. Good. So note, just to be clear, so note again that we are hashing the universe of data items and not the positions in the stream. So good. And as we wanted indeed to say, if I want item 5, then we'll show that most of the time our estimate for item 5 will come from a substream that doesn't contain any of the big elements, contain mostly the tail. And this is the answer to the question of what do we repeat order log n times. So this is the final approximate point query primitive. And by the reduction that we discussed before, this already gives you the count sketch algorithm. So we choose, so the two parameters, there's b and there's t. B is the number of buckets that we'll hash into. Think of b as 100k. So it's some constant times k, the number of elements that we're looking for. And t will be order log n. So we'll choose t random hash functions that map our universe of data items to b buckets. And we'll choose t random sign functions. And our data structure will be a t by b array. Each cell in the array will store a poly unbounded number. Each cell in the array will be the basic estimate. So the update procedure is like this. We will maintain this array of counters C. So whenever an item I arrives, we just go over all the rows of our table C, so between 1 and t. We'll look at where the rth hash function maps our ith element, and we'll just add the rth sign of that element to that particular counter. So this just means that we're running the basic estimator on the subsample, rather hashed version of the stream. Now, our estimator before was just taking the counter, multiplying it by the sign of item I, and just returning that. Well, now it does this, except it does it t times and takes the median. Any questions about the operational meaning of this? Okay. So, for example, when item 5 arrives, we'll check which column of which of the buckets it hashes to under every one of the 3 hash functions in this particular case, and we'll just insert it there with appropriate signs. Good. Good. Why does this work? Let me just state the guarantees, and I'll have to give the proofs in the next round. So first, by the basic estimate analysis, what we have is that the expectation, so like fix R, fix one of the rows of the hash table, and look at the estimate that the rth hash function gives us. Well, in expectation, it's exactly correct by the basic estimate analysis. And what is the variance? Well, again, by this basic estimate analysis, the variance is the following. Remember, when we were analyzing the variance of the basic estimate, we realized that it's just the sum of squared frequencies of all the other elements in the data stream. Okay. Well, now we're running our estimate on the subsample streams. So when I'm estimating item I using hash function R, what I get is that my variance is the sum over all other elements of the universe, j distinct from I, not over all of them, only over those that actually hash to the same bucket as I did. So this will be smaller in general, and we're adding up the squared frequencies of those elements. So this is exactly the reason why we are hashing into B buckets. The question is sort of, does this help reduce the variance? And the answer is it does. We'll do the precise analysis at the beginning of next lecture. One can sort of expect that this reduces the variance by about a factor of b, right? Because just the number of each element of the universe appears here only if it hashes to the same bucket as I under hash function R. So that happens with probability 1 over b. Okay, and then we do log n repetitions to boost the confidence. So let me just state the guarantees that we're getting. The guarantees are the following. So they take a little bit of time to parse. Suppose that we choose the number of buckets to hash into to be large enough. So what is large enough? Large enough is the following quantity. We want at least 8k buckets. But then if the stream is not very simple, in a particular sense, then we'll need more. So the number of buckets that we need to get a epsilon times fk quality of estimate actually depends on fk and just depends on the profile of the frequencies. So what we have here is we sum up the frequencies squared, so think of L2 squared mass of the tail of the signal. There's everything but the top k elements. And we divide it by epsilon squared times the kth frequency squared. We'll parse this in a second and see why this is actually powerful. Okay, so t is easy. T is just order log n because we want to drive the failure probability down to 1 over poly n. Good. So ultimately, the space complexity is order b log n for this particular value of b. And note, for example, that this particular value of b can be very large. So remember at the beginning of this lecture, rather in the middle, I said that if the stream is such that every element appears, say, once or zero number of times, or once or twice, pretty much the same number of times, then this problem is very hard. Well, and that's easy to see, because then if we look at this ratio, the sum of frequencies squared over the tail of the signal, well, that's about n, because all the frequencies are in the tail, n minus k. And fk is just a constant, so it doesn't help much. So then this means that we need to hash into n buckets. We're not getting any benefit. On the other hand, if the ratio, if the mass of the kth frequency squared is actually quite large, is at least, say, 1 over k fraction of the sum of squares of frequencies in the tail, then we'll hash into about k buckets. So indeed, in the worst case, this will require n space. Good. So just one. Then let me just say a few words about how large b is, and then we'll go to the proofs next time. Okay. So really, the interesting regime to think about is when the tail is not too heavy. So suppose for a second that the frequency squared of the kth most frequent element is at least a 1 over k fraction of the L2 norm squared of the tail. So if fk is sort of large enough, in that case, this ratio here will be order k over epsilon squared. And then we'll be able to get our approximation in order k over epsilon squared space. So the way to think about it is as follows. So think of the tail of the signal, and think of this as sort of giving you noise. And the sum of squares of the frequencies is sort of the amount of noise that you have in the system. Now you're hashing this noise into buckets. You have order k buckets. And then what matters is the following. Well, 1 over k fraction of the L2 squared noise ends up in a fixed bucket on average. And so now if our kth element is frequent enough to stick out above this noise, to be higher than the noise in L2 sense, then we'll be able to recover it pretty precisely. And if not, then the problem is just hard. Okay. So one other interesting thought experiment to do to put this in perspective is the following. Suppose for a second that our stream looks like this. There are n elements in the stream, and suppose that one of them appears with frequency root n, appears root n times, and all the other elements appear once. So if we look at what this tells us about the space complexity of the problem, we will realize that f1 squared is n. The sum of fj squares over the tail is also n. So the number of buckets that we need to hash to is actually order 1 over epsilon squared. And what this says, and this is pretty surprising, because see, we have n elements, and there's all the elements are unique except one, and this one appears only with only root n times. So if you sample an element in the stream uniformly at random, you will need to sample root n times before you actually hit this guy. So say, random sampling will not be able to even detect the presence of this heavy element unless you use space about root n. So this is exactly where the L2 notion, L2 nature of our guarantees comes into play. So using these cancellations in random signs, we're able to detect frequencies much smaller than you would be able to detect using just pure sampling. Okay. Good. So a summary. we designed a reduction that shows that if you get this primitive approximate point query that gives you a good estimate for the frequency of the ith element, then using that primitive, you can return an approximation to the top k elements, most frequent elements in the stream. And then we designed an approximate point query primitive that is surprisingly space efficient for streams where the head elements, the top k elements, actually contribute a bulk of the stream, but in this very interesting L2 sense. And next time we'll give the proofs and then go on to graph sketching and other topics.